Vectors are an important concept in linear algebra as well as vector calculus. You know, it's got vector in the name. Let's go ahead and figure out what those are. So it's pretty much arrows. So you have an arrow and it has a start and an end. Usually this is called the tail and this is called the head. All right, and they're not thought of as being in one particular place. They're just a certain direction that you travel and a length that you travel in that direction. All right, so in 2 dimensions, there's a few different ways to write these. So let's say we have vector A. We're going to put a little half arrow on top to signify it's a vector. So it might have 3 components to it. So this is more common in vector calculus. So you have, the A1 component, which is a number, and the A2 component, which is another number. And then another way to write that is as a column vector with A1 and A2. Yet another way to write that is with these things I and j. So you will have A1 times vector I plus A2 times vector j. And those I and j, they're little vectors, and they have their own meaning. So I vector is 1, 0. And the j vector is 0, 1. All right, so if you were to write this out, this is really, sorry, let me start that over. I need the A1 in front. This is A1 times this vector 1, 0 plus A2 times this vector 0, 1. Which, right, if you do put those in, you get A1, you multiply both components of the vectors, you get A1 and 0, plus another vector, which is going to be 0, A2. When you add those together, you get A1 plus 0 on the top, and you get 0 plus A2 on the bottom. You end up with A1, A2. So a little annoying, but they are useful in some places. So then from there, let's see. So you can also multiply. Well, let's see. Let's start in the graphical representation. So right, you're in XY space. And you think, okay, well, I've gone over, let's give a realistic example here. So let's do 3, -4. All right, so let me draw my little dots here. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So if I have a vector, and it's 3, -4, that means I go positive 3 units in the horizontal direction, and then -4 units in the vertical direction. If I draw that one, right, we end up right to here, and then down to here. So there's the end of my vector, and I would draw it like that, and there's the head, there's the tail. But so normally you will start at the origin, but a vector is just a vector. It doesn't have a specific place it lives. So this is going to try and draw the same parallel line, the same length. That's the same vector. And that's the same vector. And that one looks a little long. That one's the same vector. They're all the same vector because they just have a magnitude and direction. They don't have a place necessarily where their tail starts. All right. Another thing, if you multiply vectors, so if I have, let's say, vector, let's do something a little easier, 1, 2, and I'll write it in a different notation here. So how about 1, 2, and I want to multiply that by 3. All right, so I'm going to take 3, I'm going to multiply that to a vector. This is called a scalar. So essentially the scalar is just a normal number, it's not in a vector. So you have a scalar times a vector, it'll pop out a vector. And it's not that bad, you get 3 times 1 and 3 times 2 as the components. So then I get 3, 6. And what that does, if I had a vector, 1, all right, that's about 2. So this is going, 1 in this direction, 2 in that direction. There's my vector. If I do 3 times that, let's see if I can do this. 1, 2, 3. 1, 2, 3, 4, 5, 6. All right, this is going to be interesting. Oh, I almost did it. All right. This is the vector, so if this one was 1, 2, this vector is 3, 6. So it ends up pointing in the same direction, it just got 3 times as long. So this has length 1, this has length 2, this has length 3, this has length 6. All right, and we have a little bit of time left, or a little bit of space. So one more thing that we can do is, okay, well, what if you want to know the length of the vector? Well, because these things end up forming right triangles, there's a pretty nice way to figure out the length. Use the Pythagorean theorem. So we have a vector. Let's go back to a vector, and it's equal to a1, a2. I'm going to call the magnitude, the length, the modulus, has a bunch of different names, the 2 norm, Euclidean norm, Euclidean length, typically you see just magnitude or length. Modulus is a little more common. Euclidean is like Euclidean geometry, so you think, flat space, triangles add to 180 degrees for their angles. We write this usually as vertical bar, a vector, vertical bar, and it's just the Pythagorean theorem on each of the components. So I get a1 squared plus a2 squared, and then square root. Then right here, that makes sense. So if I wanted to figure out this is a right angle, this is a right angle, this is a right angle. If I want to figure out the length of this side, which is the magnitude, I would take the square root of 3 squared plus 6 squared, and that would give me the length. All right, now we'll go through this again, but we're going to go through it with 3D vectors. So now vectors in 3D are much the same as vectors in 2D, just with another component added on. So you'll have vector, A, and it's going to be a vector, and instead of 2 components, it has 3. So it's going to be A1, A2, A3, or equivalently, we could write it as a column vector, A1, A2, A3, and then equivalently, we could do A1 times vector I plus A2 times vector j plus a3 times vector k, where I think I can squeeze it up here, I vector equals, now we're in 3D, so it's 1, 0, 0, j vector equals 0, 1, 0, and then k vector equals 0, 0, 1. All right, so a1 times this vector will give you, an a1 in top, a2 times j will give you an a2 in the middle, a3 times k will give you an a3 in the bottom. You add them all together, you get a1 plus 0 plus 0, 0 plus a2 plus 0, 0 plus 0 plus a3, you get a1, a2, a3. All right, and then it's similar to how they're drawn in 3D as 2D. So let me see if I can do this well enough. All right, I did an okay job. X, Y, Z. Remember, always make sure you draw your coordinate system with a right-hand rule. So start at X, curl to Y. That's where Z goes up. And so if I want a vector, that's A1, A2, A3, or let me give a more concrete example. Let's say we want 1, 2, 3. Well, I'm going to go 1 unit, so I'll draw them all out here. I'm going to go 1 unit. In the X direction, I'll go 2 units. in the y direction, and then I'm going to go 3 units, let's see, in the z direction, and this will be my vector. So again, has a length, it has a direction it's pointing, but again, if I copy this in different places, it's still the same vector. All right, and it still has a tail and a head. All right, then from there, so similar before, if I have a constant, so let's say c times 1, 2, 3, that ends up being, I multiply c by every component, it makes the vector c times longer, so it'll be c, 2c, 3c. If I want the magnitude of a vector, so let's say I want magnitude of vector A, that's going to be the square root of a1 squared plus a2 squared plus a3 squared. It's pretty much the Pythagorean theorem in 3 dimensions. And let's go ahead and show why that's true, actually. So right, you know the one in 2 dimensions, how about 3? Well, let's say I've got my vector, and I'll try and draw. All right, let's see. X, Y, Z. So let's say I go out to here, and that's A1. And I go out to here, and that's A2. So now I've got to draw this carefully. Okay, so I've got this box. And the first thing I want to do is actually I want to figure out, well, let me do one more. So let's say that's A3. So, okay. I think that's it. So the vector we want is actually pointing from there to there. All right, and we want to figure out, how long is this thing? Well, we could solve that problem if we had that length. But the thing is, we do have that length. So this length here, right, this is A2, and this length here, that's A1. So I want this length right there, that's going to be the square root of A1 squared plus A2 squared. So now I know the length of this one, and so now I have a different one. So if I draw this just in kind of this plane where this triangle exists, then I'll end up with my dashed line here. I've got my vector, and then I've got my other dashed line. This length is A3, this dashed line right here. And then this one right here is the square root of A1 squared plus A2 squared. And now I have another regular triangle again, not some, rotated one in 3-dimensional space. I can calculate the magnitude of this side. So the magnitude of this side is the square root of this piece, square root A1 squared plus A2 squared, right, that's the entire length, and I squared the entire length, plus A3 squared. But if I simplify that, right, if I square the square root, then they essentially cancel. So that's the same thing as A1 squared plus A2 squared plus A3 squared. And so there, that's how you get the Pythagorean theorem in 3 dimensions, and then it continues on to 4 dimensions, 5 dimensions, and so on. All right, anything else I'm missing here? No, I think we're good, so let's continue on how to add vectors and what that means and what it looks like, and also adding negative vectors. All right, so last little bit is adding vectors, subtracting vectors, and geometrically. What does that mean? So right, let's say I have vector A, and I add that to vector B. Well, component-wise, you add the different components. So that's going to be A1, comma A2, plus B1, comma B2. If I add the vectors together, then I add A1 and B1, that's the new horizontal component, so A1 plus B1, comma, then I'm going to add A2 and B2. And that's the new vertical component. All right, and similar in 3D, I'm not going to write it again, but you have 3 components, you add them element-wise. All right, well, let's look at, adding vectors together. And let me make that a little more down. All right, x, y, and let's do 0, 2, and looks about right. 1, negative 1, and 2, 3. So if you want to add vectors, that's not very hard. So we can actually add, let's start with 2. So let's do 0, 2 plus 1, negative 1. And there we go. X, y. So the idea is we're going to take the vector here, we're going to start at the origin for the tail. We're going to go up 2 units. Okay, let's pretend that's 2 units. Then we're going to add to that, we're going to put the tail of this vector on the head of the previous one, and we're going to go in the direction 1, negative 1. All right, and then if I've drawn this kind of well, that ends up being 1, 1. So that's kind of the idea. You can just add vectors onto each other. And right, if I were to calculate this out, it's 0 plus 1, so that's 1, and 2 plus negative 1, that's 1. And right, so we did end up in the right spot by adding them like that. All right, it's a little more confusing if you subtract vectors, so let me just do that over here. So let's say I have vector 2, 3 minus vector 0, 2. All right, so geometrically, the minus always trips me up because I have to think, okay, well, it's going in the reverse direction, and then I have to, keep that in mind, and, it just messes me up. So instead, I like to think of it as 2, 3 plus negative 1 times 0, 2. All right, and what this ends up doing is it makes the vector go backwards. It goes in the opposite direction. I think that's how you spell opposite. And so then if you add those together, right, instead of a subtraction now, I have an addition with a vector going backwards. I have vector 2, 3. Okay, that kind of looks like 2, 3. And then I'm going to take my 0, 2 vector and I'm going to flip it, right? So it's going in the opposite direction. And so that will get me down to there. And I haven't drawn this well enough to guess that. Maybe I did. So that ends up being 2, 1, I'm pretty sure. And right, if we do write this out, it ends up being, okay, 2 minus 0, so that's 2, 3 minus 2, that's 1. Okay, I did draw it well enough to guess. But that's how you add negative vectors together. And then if you add, 3 vectors, so let's go ahead and do that. What if I do 2, 3 minus 0, 2 plus negative 1, negative 1? All right, well, I'll start out with my 2, 3. So, oh, sorry, it's the wrong one. Sorry, 2, 3 is over here. All right, and then I'm going to go the opposite direction of 0, 2, so flip it, so it's going down, so 0, 2. Then I'm going to add 1, negative 1, which points that way. So you can't rely on drawing anymore, but I think I got that right. We compute all these out. 2 minus 0 plus 1, that's 3. 3 minus 2 plus negative 1 is 0. And so yeah, I think I did get that approximately in the right spot, right? That was 2. So this is 3. Yeah, I think I got it-ish. Almost. But that's the idea. So adding vectors together, fun stuff.